Okay, I think we're going to get started. So welcome everybody to the Snug. I know we've been having this intermittent here. My name is Scott Northrup, one of the analysts here at SciNet, and today I'm just going to give you a quick overview on the Niagara system. I know it's been bated breath. We keep saying waiting, it's coming, and it's slowly coming. We're getting there. Most of the configuration and setup is pretty much done. The contractor Lenovo is just finishing up the last bit of testing, kicking the doors, and we're going to have it the next couple of weeks to get our configuration set up, and then hopefully have some early user access. So for you guys to be able to get on before we, so you can get in and actually start working on it a little bit. So today, mostly this first little presentation, just a presentation I did a few weeks ago, as you can tell by the date, just overviewing some of the hardware features, some of the details of it. There's not a lot of specifics from a user perspective, but it is interesting just to see what's built in the system. And it'll give you a perspective once you start to use the system, what's different about this system as opposed to the previous GPC. And this can be pretty interactive. I've got some pictures and stuff in there, but this is only going to take probably 20 minutes, half an hour, and then feel free to ask your questions and stuff. Some of the details we haven't, about software setup and exact details, we're still sort of working out. But the short answer is that we're trying to make this, for people who are familiar with the GPC, migrating to this system should be relatively straightforward with a few little differences with the scheduler and some of that. But in general, it shouldn't be too painful. Okay, so just to take you guys back, if those aren't familiar, basically about a year ago, we put an RFP out for a new system. So there's a part of 3 or 4 years ago, the plan was to come up with these 4 new systems for Canada. There's the 3 GP systems. This is Cedar, Graham, and there's a new system. I guess I can call it Beluga now anyway. It's at McGill. These are sort of the general purpose systems for your small, medium serial jobs, sort of GPUs, the whole sort of catch-all. The Niagara system was called LP, or large parallel. Basically, it's supposed to be a system for the big jobs. So designed to run, your 1,000 core plus up to 20,000 core, large scale, really high network speed, that type of thing. So it's targeted for that. Doesn't mean it can't run smaller jobs, but the target obviously will be for the big stuff. So it's designed for large MPI jobs. It's a competitive RFP process. We used a series of benchmarks to test this out. Network design was important, storage performance, like the real classic HPC high performance type stuff. There was 11 original bidders, and then Lenovo ended up being chosen. And the system specifics, it's basically 1,500 nodes or 60,000 cores. Each node has 40 cores, and they're the latest generation Intel Skylake. So it's an x86 system, so it's nothing too esoteric. It'll run Linux, just a newer version. So from that point of view, Intel compilers, very familiar. There's about 40 racks, 60,000 cores total. There's a lot of memory in these nodes. There's 192 gigs per node. So we're not so worried about our old 16 gigs per node anymore. You have a little bit more room in this, but there's 40 cores too, right? So a little over 4 gigs per core, but there's quite a bit of room in each of these. These are fatter nodes. As you notice, the original GPC was just under, just over 3,000 nodes. This is only 1,500, right? So it's actually less in that sense. It is an InfiniBand network, so very high speed, low latency, similar to what the GPC. However, it's a much more higher performant network in the sense that the QDR and DDR on the original one was a highly oversubscribed network, which worked fine, but has issues when you scale up to high numbers. This one is designed much more for, if you wanted to run all 60,000, you could, and you get a nice, good cross-sectional network in it. So if you've got really big codes that are doing high bandwidth and scaling, there's an interesting configuration called Dragonfly. I'll get into a little bit about that, but it's more from a network topology point of view. From a user's perspective, you won't even notice the difference, but it is interesting. That's how we scale up to a large number of cores without the cost that you would, and we'll talk about that in a little more detail. Scratch and project will be about just under 10 petabytes. This is our GPFS, but it's a much higher performing one than our current one. So that was always an issue in SciNet, was our Scratch performance was a little bit anemic. In the early days, we'd always have issues with, somebody's hammering the file system, and it's still an issue. Every file I/O is always a problem, but this system is a much more performant out of the box. So instead of 5 to 10 gigs a second, this one should be 60 to 90 gigs a second for the whole system. But it's a bigger system, so 60,000 cores too, right? So you can always, don't abuse the file system, but hopefully this will be. Now, in that vein, we do also have a new feature adding into the system called a burst buffer. And so this is a smaller amount of storage, but it's really high performance. These are SSD and NVMe drives, so very, very specific high performance. This will be a different tier, and this is not meant for long-term storage. This is just meant for kind of like how we always point you to use DevShmem or something if you need to use a little stuff, but this is shared. So it can be shared, you can write, you can do your checkpoints. If you're doing I/O type stuff, you're a little more free to abuse the system because it's designed specifically for that. We will probably rate at the initial, how this is going to be configured, about how you'll get access and purging policies and all that will be determined. But from a hardware perspective, basically it's a much higher performance tier layer that's not meant for long-term storage. We're talking 24 hours, stage your job, run it, pull it out, big database. But it has the flexibility of being available to all the nodes. And it runs just like you would off scratch or home. However, you have that high performance storage. And it also won't bang up this file system. So if somebody's doing something, really high IOPS or something, or you're doing really large checkpoints, or you want to run a really big job, you can do that there. So it's sort of decoupling that. And right now we're going to do that in sort of an explicit thing. It may be added in the schedule or that type of thing, but it does have that capacity. So sort of feeds and speeds, the overall R peak of the system, that's the theoretical performance is 4.6 petaflops, which you're not really going to get on a modern system. Actually, the HPL number on the system, we're getting just over 3 petaflops. So that's pretty good. That's about 10 times over what we get out of the GPC. And if we look in terms of flops per watt, it's about 20 times more efficient. So it's sort of per dollar kilowatt hour operational cost, the system, you're getting a lot more in this general. But that being said, this is 9 years newer, right? So I would hope we've made a little bit of progress in that time period. Yeah, so the RMAX, we just get just a bit of over that. And as I said, this is about 60% of what the power draw of what we were getting out of the original GPC. So the original GPC was 45 racks by Dataplex. This system is 21, so it's denser. It's similar, just half the size. And why didn't we build? We would love to build a bigger one, but given that we actually had about half the amount of money to buy this system as well too. So things scaling. So that's the overall major specs. But from a first blush, basically they're just fatter, bigger nodes, still x86. So the ecosystem that you're familiar with. You should recompile your code when you're going on here, but it's still GBFS. It's still the same sort of idea. It's just going to be you won't have to worry about network performance as much on this system. And you've got to, if you're doing smaller jobs, you now got to think in terms of 40, no longer multiples of 8. You want to think into scale well. And if you're doing more serial type workload, you've got to package it into. We're still scheduling by node, but those nodes are now a lot bigger. So you want to use. There's a lot more. There's 5 times as much resources in one node. Okay, so the basic node, as I said, is an ST5. It doesn't really matter. Basically, it's an Intel Skylake. That's the particular gold brand. It doesn't really matter. But as I said, we've got the memory bandwidth on Skylake is a big jump too. That's one thing. When we got the original GPC, we waited for Nehalem that generation because there was a big bump in memory bandwidth. And that was about 30 gigabytes per second. Now these systems, you're like, well, 150. Well, that's great. Well, but it's also 20 cores for each of those as well too. However, this will help with anything that's sort of memory bound codes. This is actually a pretty good bump over the Broadwell. So those of you who've been running at Graham and Cedar, they have 1 generation older, pretty good chips, but they're the Broadwell based, and they only have just under 100 gigs a second. So these memory bandwidth goes to 6 channels. So it just means it's better for anything that's memory starved. It should help from that point of view. And these also, the other big change here is these are AVX 512 capable chips. This is the instruction kit, a fatter vector instruction unit, as opposed to AVX2, which was 256, so it's double the length. So if you have really nice big vectorized codes or you're using MKL, BLAS libraries, that sort of thing, you'll probably also get a boost from that. Because this was a feature they added original in the Xeon Phi line, but now it's in the standard Xeon chips as well. And just to be pointed out, this Skylake chip is just a generic Xeon. This is not a KNL, it's not a GPU. This whole system is a stock, just regular HPC computing CPU type setup. So there's no, yes, they're bigger nodes, so threading is important and that type of thing, but it still follows in the model of just traditional homogeneous computing here. Yeah, so we have 1 EDR connection per node, and then they're connected to this Dragonfly. But they're stateless, same idea as the previous one. So we lose the node, we reboot it, runs the same as the other one. That's a picture. They're just fatter, not really much that interesting. One thing is the power draw on these CPUs is getting higher and higher. They were about 95 watts, now they're 150 watts. So the air cooling these is getting harder and harder. And you can also notice from a memory point, there's now 6 DIMMs per chip, where there used to only be 4. So it's just that's how they get the memory bandwidth, is they just stripe them in parallel to get more. But it's just a simple diskless node, doesn't really matter. There's 4 of them in a node. I'm going to talk quickly about the network stuff, because that's one of that and the burst buffer are sort of what separate this apart. I guess I would call those are sort of distinguishing features that would make this system a little bit different than the other sort of GP systems. So this Dragonfly topology is an interesting topology, and it's basically the idea is to get a very large cross-sectional bandwidth of the network. So as ideally 1-to-1 what we'd like. Ideally, I'd like all my connections to have a connection to everybody else at a 1-to-1 speed, right? So that I don't have to go through switches and this type of thing. However, that costs a lot, because the more as I grow my system, I need more switches, I need more cables, all this type of stuff. So they've come up with these different approaches. One of them is called Dragonfly, and this basically uses sort of some adaptive network technology, and actually maybe the picture shows it easier, where basically what we do is we make groups that are 1-to-1, that are smaller, that are cheaper within switches, and then we use so if there's, say you needed 100 connections out, we actually only use 25, but we can make those 25 act like they're 100. So it's sort of, instead of basically using, because if you're running a job, you're not likely using all the network at once. So this is sort of like congestion traffic control, where instead of it saying, okay, all the traffic must go down these 2 lanes, I'm going to send some traffic over here and send some traffic over here, and the net benefit is overall. Now, I don't want to control it, and you don't have to either. This is well buried underneath in the fabric manager, but this allows us to use less hardware more intelligently to scale up to larger nodes. And if any of you familiar with sort of network topologies or supercomputing in general, you've probably heard of the latest generation of Cray, the XC4050, at various sites around the world, and that is based on using this topology. It's a different hardware, but from a software point of view, they've been using this topology. It's new to InfiniBand, sort of taking InfiniBand's sort of commodity and stuff. So they've taken this proprietary approach and applied it, onto generic hardware. And we're one of the first ones applying this, right? But it actually allows us to build a very high bandwidth and efficiency network with less hardware, so it makes it cheaper, basically. So it has some advanced features like adaptive routing and congestion control. This is new for InfiniBand. We may talk about this a little more. Right now, this is supported in OpenMPI, so you just compile your code, you don't have to know the differences. There may be some tuning features for those of you who are using FFEW libraries and stuff as we get along and you want to just look at the performance. We can talk about that more specifically. We're sort of getting into this stuff too. They have a new technology under the hood for those of you who are playing with the MPI stuff. But for most users, you'll just go MPI run -np whatever, and you won't worry about it. It'll just work, and that's usually the idea. But that is one of the distinguishing features here. So that's a picture of the topology. This is actually a specific topology. Our system is a Dragonfly in 4 wings. Effectively, there are 4 groups of 432 nodes, so 16,000 cores. So you can kind of think of, if you're within that one group, you basically have a 1-to-1 network, right? So for most of you, for medium-sized jobs, you'll probably be within that one of those individual groups, and so it won't really matter anyway. But that's just sort of the general topology. The nice thing about this type of network is it's very scalable too. When you use fat tree type networks, when you want to build out more, you start having to put higher level switches in. This one, because of the nature of how you're adding on blocks, if somebody has some extra money, we can easily add on to this network and scale it out relatively easy too. So that's a nice feature as well, because it's all built out of edge switches. So storage, main storage is our traditional just GPFS disk-based storage, mechanical storage made with 10 terabyte drives. It'll be about 10 petabytes available. This will be Scratch, home, all your traditional space, but it's 70 to 90 gigs per second. So pretty good bump up from just that throughput. And this all sits on that higher speed network as well too, using that network. So it benefits from that as well too. There is an Ethernet network on the system, but it's only used for management. So everything else is done through the InfiniBand. And I mentioned the burst buffer. So this is just made with 10 nodes of these really high performance NVMe drives. If you've gotten a latest generation laptop, you probably notice you have a little stick of memory that looks like that's actually your hard drive. This is similar, just scaled up. They're bigger drives. And this sits on a system called Accelero. It's a proprietary software they have that basically takes all these drives from a bunch of different servers and make them look like a parallel file system with the GPFS. But it's very good bandwidth, but where it's very important is IOPS. These seeks and reads and writes. So any of you guys that sort of we've yelled at before for having very IOPy code. First, fix your code, and then if you really need to, this should help. This should help with all that type of stuff. But once again, it'll just appear to like GPFS. You can just use it directly. There's no third-party API you have to use. We have this sit up just like a regular file system. But it's significantly smaller, so of course it's not there for long term. It's just meant as an intermediate layer. So yeah, so the burst buffer really just, this is where its model is it's somewhere between memory, and the parallel file system, in sort of the pyramid of file systems. So the performance is not quite as good as memory, but it's somewhere in the middle. And if you need to do ILO, it's parallel across node. The thing about this too is, if you can get away, if you're only running single node jobs, now those big nodes have 192 gigs of memory. Great, use the DevShmem. But if you're doing some checkpointing or across different nodes, this will help you. Another tool to use if you're having performance problems. This is just details about the NDI Mesh that goes on Earth. I'll just skip that, but it's basically all, at the end of the day, it looks like a GPFS file system on the top. So of direct interest to most of you guys is probably the software configuration. What, from a user's perspective, is this system going to look like? Well, it's Linux. It'll just be a newer version, CentOS 7. How you access the system will be a little bit different. Right now, there'll still be a login node, but right now you've always traditionally just used your SciNet login. Well, it'll still be the same username, but the password will be based off of the CCDB. So it's your top level. They're sort of flattening out all these individual consortium accounts. So any ones you've logged into Graham or Cedar, you've just logged in, and that same level, it'll be the same here. So we're sort of flattening out that level. So it'll be the same idea there. We are going to migrate your existing accounts. So if you have file systems and stuff on the GPC, that will go on. So your usernames will be the same. There might be some little bit details under the hood that we're still working out, but it will be pretty straightforward from that point of view. Modules and stuff, Ramsey might talk about some of that, but we're not going to have we're not just taking the old software stack and just dumping on there because a lot of it's ancient. We'll migrate a lot of it through, so it'll still be the Intels, the compilers, all these different pieces. So some of those pieces will be available. We will have the Compute Canada software stack with maybe a few little tweaks available. So so a lot of that software that's built on Graham and Cedar will be available. Maybe not as an default configuration, but you may just load it and you'll be able to use it. But still the same old module type approach. So maybe slightly different, a newer version of all that, but it's the same feel. One of the biggest differences, users, there'll be a little difference, is we're no longer using Moab Torque. So your submission scripts will be a little different. Same idea, just a slightly different syntax. So it's the same idea, submit a job. Now, instead of going -l ppn equals 40, it'll be nodes equals 1, tasks equals 40. But this is similar to Graham and Cedar, but much simpler because our system, 1,500 nodes, they're all homogeneous, no GPUs, much shorter, but it will keep the same sort of limits, the 48-hour limit, that sort of type of thing. It's just the only difference is you just can't take that shell script you had before. You'll have to change that. You could use the same shell script, but you probably have to change some of the environment variables and the stuff at the top. It's one of those ones, you'll figure it out, and then you'll just use it. We'll put some examples on the wiki. Shouldn't be too bad. Yeah, as I said. And then there's the fair share allocation stuff works the same. It'll be based on the rack allocation as you're familiar with on the previous system. It'll just be on the newer system as opposed to on the older system. So a lot of it should be fairly familiar, just with a few little tweaks as the newer system. And hopefully overall better performance and this type of thing. One thing too, we're getting rid of, right now we have a two-step login process. You go into a login node, then you go into the devel node. That now will just be one. So we can simplify that process too. So you'll just log into the login/devel node. Because that was originally set up because we had multiple systems. We had the TCS GPC. Now it'll just be you log into Niagara or you log directly into the development node. Once again, there's just minor variations. We're just trying to streamline the process. But it shouldn't take too much to get up to speed on this type of stuff. This is the newer system. The old system was in 3 big rows. Now the new system is just in 1 smaller row. It's 21 racks, and they're all smaller, but still same water cooled. This is the older equipment. There's new management. This is where the TCS was down here. Now that's where the new management row goes. Doesn't really matter too much, but it's just for those of you who've ever been to the data center, that's some of the configurations. The rest of this is just sort of pictures we've taken. We had, if you guys followed, we removed the TCS back in September. Then we removed part of the GPC. This is sort of the pictures of the process. So this was the actual TCS, pulling all the nodes out. Even without the nodes in these TCS racks, they still weighed 1,400 pounds. That was they weren't kidding when they're talking about heavy iron. A full rack of one of those TCS nodes was 3,700 pounds. So yeah, I've got the e-cycling retrieval for 40,000 pounds of e-cycle material to remove anyway. So this was the GPC racks. So we removed 21 racks of that. to make room for the new system, and then once we get that up and running, we will decommission the existing ones that you guys are currently using. But that was just pulling it all apart. It wasn't quite as much work, a little more modular than the TCS was, but it still lots of stuff. And all this stuff was basically e-cycled. This nobody really wants. It's not cost efficient to run this older stuff anymore. So that was the empty space that we cleared out. This is the new management row. It looks like more black servers, nothing too exciting, but this one here is the new storage. So that's about 4 petabytes in there. This is the burst buffer. There's some switches. It looks like computing equipment, but it does its job. This is the Dragonfly network, empty. These are the main 3 core switches. There's a bunch of copper cables on the edges, and these are all the blue ones now, are all the long links. So as you'll see the next picture, it gets a little more complicated because there's 1,500 of these that run out. So the installers were not happy with me, but in terms of it, cost-wise, it actually does scale out much better. So these run out to all the other compute nodes. This is the actual compute rack. There's 72 of these compute nodes in each one of these racks. As I said, there's four compute nodes in each one of these sort of 2U configurations. But it's a slightly different variation, but it's just x86 servers, and a lot of them piled together. And these are water-cooled with a door, just like the previous generation. So there's the door. This is a door open, and you can see that's the wiring in the back, which don't touch because I don't want to break anything. But yeah, it's pretty straightforward. So that's the new stack of rows, 21 of those cabinets if you walk in just in the data center, all lined up. And it's in a much denser form factor than the previous one. Just that's the newer generation. I do have a little bit of a time lapse, but let's see if this works. Find it. Oh, there it goes. So this was a movie. There's no sound on this one, but it was basically just a bunch of time lapse from some pictures that we had from the deconstruction of the system, as well as some of this. We have all these IP cameras, so we took some of that footage, and Marcelo coupled it all together. So here you can see moving the TCS. The wires under the TCS was just a nightmare in terms of all the old hard copper cabling and stuff. But there was literally kilometers of cabling that got pulled out of there. And so then this is, you can start to see in the top corner, this is starting to pull out, starting to set up the management. This will switch a few different, yeah, here's from the other angle, you'll see it a little better. So this is where the TCS used to be here, and then there you'll start to see some racks. You'll see them tear up. It's funny, watch these guys. They'll put a cable tray in 3 times. They actually move it. They set it up, they took it apart, and they put some new stuff in, and they kept, because this is all the old cooling infrastructure, so they had to kind of work around it. And so then they moved it again. So you'll see this cable tray move again. This is actually what the shutdown I sent a message about tomorrow is we actually do, this was on temporary power, and we actually have to do some final power modifications on that system. But anyway, it's not that interesting, but it is, it's kind of neat just to kind of see all the pieces come in. So this was all the management infrastructure that got set up there. We have 2 more of these. Right now, we just have only about 4 petabytes. We have 2 more of those that are coming in this month that'll expand out to bring up to our rest of our storage. So this is flipped around the other direction. This is the end of the iDataplex racks, and so this is just the old compute racks as we're starting to phase those out. So you'll see them. These are starting to be decommissioned. So this is pulling all racks and racks and racks of the compute nodes are pulled out. Then finally the racks get pulled out. And this was about just under. It was just over 40,000 pounds, or 20 tons by the end. So that was empty. And so then we started doing all the orange are the old InfiniBand cables, and the new ones are all green, so at least they're different colors, so we know which one's which. Yeah, so you can kind of see it off in the corner here, the angle. They're starting to set up the plumbing and set up, and then the new racks will start to come in slowly. But you can see the green wax they're laying out, and then this is laying out a lot of these new fibers, because they had to bundle these in groups of miles and miles of fibers, right, to get that all set up. That's the biggest work. The racks actually come fully assembled from the factory, but actually the cabling is the stuff you can't do and stuff. So that actually is the biggest sort of. There's about 100 man hours of just cabling to get that all sort of Plumbing's all under the floor, yeah. So you can, when we pop that, there's an 18-inch raised floor, so about 1.5 feet, and all the plumbing's under there. So the tubes, you just pull up the tiles, and you can adjust it. That's why it makes it fairly flexible. You just pull up tiles and adjust it. And a lot of this is actually, because it's similar, it's using a lot of the existing plumbing, just different hoses, but it's the same setup as the other iDataPlex. So it literally was easy, even the same electrical. Yeah, 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 just for the new stuff. So this is some of the new racks being, so 3 of them set up. See there's the doors in the back. But you can see these cutouts here where we just adjusted the tiles. These are 2-foot tiles. It's all meant to be pretty modular. And so then this is relatively easy to swap stuff in and out. So that's, you're paying, so it's to avoid, infrastructure rechanges. So the racks you can see come in fully loaded, almost fully loaded. They're a little too heavy, so they have to actually ship a couple servers extra because they're too heavy to ship them fully loaded. But mostly, I think 60 of the 72 come in the rack. Then they actually have to populate the rest in place. So this is just some of the, as you can see, here's some of the plumbing going on, just redoing some of the electrical, and then that's a flat of the servers that don't come pre-installed. They've installed and then de-installed basically. So then this just rinse and repeats for 21. Most of this was done just before Christmas, the last rack arriving just December 21st or something. But then over the last month, they've been, fixing the system, like setting it up. There's a lot of burn-in, broken hardware, that type of stuff, and getting that all accepted. So that was going on. Yeah, so I think this is the last little bit, just with, you can kind of see. They finally remembered to close that one door over there. Anyway, as I said, it's just for those of you who haven't seen the data center or haven't seen how this all goes together, it's really just individual compute components are not that interesting, but as you scale this up, the cabling and all the details, it's a scale out problem where you start to have. And this system is relatively small compared to the other one. It's not small, but it's smaller. It said about half this, so that was the end of that one. We don't need to revisit that one. There you go. Okay. So thanks for Marcelo to put that together. He did quite a bit of work stitching all this information. We'll probably have a more polished version of that put out just for like PR. So timeline, we started this about a year ago. We're down here around now. We're deploying it, should be almost finished now. We'll do some test and config in the final storage configuration. As I said, we'll come in the end of March, and we should have the system in production. And the other GPC shut down just around April. So that's sort of our rough timeline. I mean, over the next month, you'll get some emails from us about when users can get on and that type of thing, beta configuration and that type of stuff.